Hi everyone, in the last lesson you learned how to simplify radicals using numerical radicands. This time around we're going to learn how to simplify radical expressions where you will have variables underneath the radicand. But before we get started with that lesson, I would like you to please go ahead and solve these two equations. The first equation is x plus 7 squared equals 24. And the second equation is 2w squared plus 13w equals 7. Both of these are quadratic equations, and they require different approaches for solving them. So I want you to pause the video and solve each of these equations using skills that you have learned in the past. And when you have an answer, please go ahead and restart the video. All right, for the first problem, we have ourselves a parenthesis squared. And what we can do is eliminate that parenthesis squared by taking the square root of both sides. When we do that, the square eliminates the square root, leaving us with x plus 7 is equal to plus or minus the square root of 24. So looking at the square root of 24, we need to think to ourselves, what is a perfect square number that can go into 24 evenly? And whenever I think of 24, I always think of 4 and 6. So this is x plus 7 is equal to plus or minus the square root of 4 times 6. The square root of 4 is 2, so this is x plus 7 is equal to plus or minus 2 square roots of 6. Now I'm going to subtract 7 on both sides, and I have my answer of x is equal to negative 7 plus or minus 2 square roots of 6. And that is your answer. You do not need to simplify it any further, since the square root of 6 is something that where we would be working with a decimal. Don't worry about it. We'll just leave it just like that. For example number 2, this is a different type of quadratic equation. For this type of quadratic equation, I would recommend bringing the 7 over to the other side and making it equal to 0. So we have 2w squared plus 13w minus 7 is equal to 0. Now we have ourselves a trinomial, and let's go ahead and factor that into two parentheses. So I'm going to split apart the 2w squared into a 2w and a w. And I'm going to look at the factors of 7, which are 1 and 7, and my goal is to get a 13. Now I'm going to try 2 times 7, I know is 14, and 1 times 1 would equal 1, because there's a 1 right here. So 1 times 1 is 1, and so I know that a 14 minus 1 would equal a 13. So what that would mean is I would need my 14 to be positive, so I would multiply 2 times a positive 7, so 2 times 7, and then I would need a negative 1 inside. So 2 times 7 is 14, 14 minus 1 is 13. So my zeros, essentially, to solve this equation would be 1/2, or w would equal negative 7. And that's just identifying the opposite of what's inside of each parenthesis. So hopefully you've got both of these answers correct. If you struggled with the warm-up, please make sure that you come and see me after school sometime so that we can discuss how to solve these types of equations. Because these equations are not going away, they will be on your final exam in January. So I want to make sure that you feel comfortable with these, with solving these types of equations. So our learning targets for today is to be able to say, I can simplify radical expressions with variables. So all of our expressions this time around will have variables inside of them. And there exists a shortcut and a trick in order to make this process very easy. The next thing is I can add and subtract radical expressions with variables. And then one more thing that we're going to do is we're going to be doing a real-world problem working with perimeter and area as well. So that's another thing that you should be able to do by the end of this lesson. So it says, the properties of rational exponents and radicals can be applied to expressions involving variables. Because a variable can be positive, negative, or 0, sometimes the absolute value is needed when simplifying an expression. So whenever you're working with an odd number, if you're taking the odd root, you could end up with a negative number, or you could end up with a positive number. And whenever you're taking the even root of a number, we typically are working with a positive number, or the absolute value of it. Because this is complicated, long story short will be this. Assume all variables are positive. in every single problem that we're simplifying. So please assume all variables are positive. Otherwise, it's too complicated, it gets messy. You can worry about the absolute value when you get to pre-calc. That's something that you'll be working with when you get up there. But in the meantime, in Algebra 2 with trig, we will assume that all variables are positive so that we don't have to deal with that absolute value. So for this lesson and for the rest of the problems where we'll be simplifying these types of expressions, just assume your variables are positive. So we're going to simplify our expressions, assuming all variables are positive, and we are not going to be allowed to use a calculator. So please keep that in mind. Every single one of these problems, I will not allow you to use a calculator. Notice that all of these problems are circled. So the ones that are circled are the ones that I'm going to do in this video. The ones that are not circled are going to be problems that I'm going to do in class. Because there's so many problems, I want to make sure that I touch base with you when we're in class and do these 3 problems. I recommend strongly you trying them on your own, especially after I've gone through a lot of them. And at any point in time in this video, if you want to pause the video to try some of these on your own, please feel free to do so, especially if you can see the pattern right away. Otherwise, here we go. So the first thing that we have for letter A is we have 200, or the square root of 200 x cubed y to the 4th z to the 7th. There exists a shortcut, and I'm going to show you that shortcut after I've shown you the long way. So what this means is whenever you think of the number 200, hopefully you think of 2 times 100. So I'm going to break that down into 2 times 100. Then I have x cubed, and what that means is that I have x times itself 3 times. Then I have y to the 4th, and what that means is y times itself 4 times. Then I have z to the 7th, and what that means is z times itself 7 times. One, two, three, 4, 5, 6, 7. All right. That's a lot to write down, but watch what happens. Since this is square root, as soon as you have a pair of something, you can bring it out of the square root symbol because it technically means something squared. So I know that 100, like the square root of 100 is 10. So that's going to come out of my root. So I'm done talking about that. The 2 is going to stay inside of the root. So I'm going to leave a little bit of space, and I'm going to write down that I have 2 inside of my root. Then, anytime I have a pair of something, it will come out. Like x times x really means x squared. And the square root of x squared is x, so out will come an x. I have 1 x left over, so 1 x will stay inside of the root. Next, I have a pair of y's, so that means that that's y squared, and the square root of y squared is a y, so out will come a y. I have another pair of y's, so that means out will come another y. Then I have a pair of z's, so out will come a z. Then I have another pair of z's, so out will come another z, excuse me. Then I have another pair of z's, and out will come another z, with 1 z left over. So my final answer is going to be 10x, this is y times y, which is y squared, z times z times z, which is z to the 3rd, times the square root of 2xz. And that is your answer. Now, ladies and gentlemen, you probably are thinking, wow, that's a lot of work. There's got to be a shorter way. And there is. The shorter way is to use the fact that this is a square root and that there's an invisible 2 on the outside. So what the shortcut is this. You'll still have to work with the number just like I did here. 200 is 2 times 100, and the square root of 100 is 10, and there's going to be a 2 left over. So we work with our numbers like normal. Then we work with our variables in a very strategic way. Watch this. 2 can go into 3 one whole time. So notice that 1x came out. 2 can go into 3 one whole time with 1x left over. Left over under the root is 1x. 2 can go into 4 2 whole times with nothing left over. Notice that 2 can go into 4 2 whole times, and 2 y's came out of the root with nothing left over. Then 2 can go into 7, can be divided into 7 3 whole times with 1 left over. So we had 3 z's, or z to the 3rd power, come out with 1 z left over. And that is the shortcut. So if we were to look at letter B using that shortcut, here we go. So looking at, we're going to work with the number 32 and ask ourselves, are there any perfect cube numbers, because this is a cube, perfect cube numbers that can go into 32? And we do have one. It's an 8. So this is going to be the cube root of 8 times 4. And then I'm going to write x cubed and y to the 6th. So the cube root of 8 is 2. I'm going to have a 4 left over, so I'm just going to cross that out. 3 can go into 3 1 whole time with nothing left over. 3 can go into 6 2 whole times with nothing left over. So I took care of the x's, I took care of the y's. What's left over is a 4. So my answer is 2xy squared times the cube root of 4. And that is it. That's your answer. There's nothing more for you to do. 4 is a perfect square number. It's not a perfect cube number, and there's nothing further for us to break down when it comes to the number 4. Let's look at letter C. For letter C, 6 is not a perfect cube, and it doesn't have any perfect cube factors. So 6 is going to stay inside of the root. Now I'm going to use that trick. 3 can go into 4 1 whole time with 1 left over. So I'm going to leave like about a finger of space, and I'm going to write cube root. And so far I have a 6 in there. 3 can go into 4 1 whole time with 1 left over. 3 can go into 9 3 whole times with nothing left over. So that's y cubed. 3 can go into 14 4 whole times with 2 left over. I know that 3 times 4 is 12, and 12 plus 2 is 14. So that's all I'm doing, is I'm essentially, how many times can 3 go into 14? That's 4 whole times with 2 left over. And this is your answer, xy cubed, z to the 4th, times the cube root of 6xy squared. Let's go ahead and look at letter D. For letter D, there is something that's common that we use often, and that you might see often, and that's 625. 625 is 5 to the 4th power. 5 to the 4th power is 625. You could work with 25 squared. That's not a big deal. You can break it down like that, but this is something I would recommend that you know, that 5 to the 4th power is equal to 625. So I'm going to write this as the 4th root of 5 to the 4th power times z to the 12th power. 4 can go into 4 1 whole time, so I have 5. 4 can go into 12 3 whole times with nothing left over, so that's going to be 5z to the 3rd power, and that is your answer. The 4th root goes away because there's nothing that's left over. We've already simplified it completely. Let's go ahead and look at letter E. Letter E, we are raising 36m to the 4th n to the 10th power to the 1/2 power. So I'm going to distribute that exponent to every single term, including the number. So this is 36 to the 1/2 power, m to the 4 divided by 2 power, since I'm just multiplying, and n to the 10 divided by 2 power. Do you have to show this step, or can you go straight to 2 and 5? Absolutely you can. With respect to the exponents, that's perfectly fine. 36, this is equal to 6 squared raised to the 1/2 power. This is m squared, n to the 5th. And the exponents will cancel out here, leaving us with 6 m squared, n to the 5th power. If you can go from the very beginning of this problem to 6m squared, n to the 5th, just like that, like really quick, that's not a problem. You don't need to show this work in between. I'm going to let you guys try letter F on your own, or, well, I'll be doing that in class the next time I see you. Let's go ahead and look at letter, and same thing with letter G. So let's go ahead and look at letter H. For letter H, what we have here are 2 cube roots that are being multiplied by to each other. Excuse me. I'm going to simply multiply them. So I'm going to combine and make this one cube root. So what that's going to equal is the cube root of 6 times 18, which is 108. X squared times x to the 6th, we add our exponents, so that's going to be x to the 8th power. And y to the 5th times y to the 4th, 5 plus 4 is 9. Now I'm going to work with the number 108. I don't know a lot about 108, so what I'm going to be looking for is I'm going to break down 108 and stop once I find a perfect cube. So 108 divided by, I'm going to try 2 because it's an even number. 108 divided by 2, it's going to be 54. And I'm going to break 54 down. 54 divided by 2, that's 27. I'm going to stop right there because I know that 27 is 3 to the 3rd power, and I was looking for a perfect cube, and 27 is certainly a perfect cube number. So I'm going to rewrite this as the cube root of 2 times 2 times 3 to the 3rd power. So 2 times 2 times 3 to the 3rd power. And then I have x to the 8th and y to the 9th. So anytime I have a grouping of 3 or anything to the 3rd power, I can eliminate it. So the 2 2's are going to stay inside of the root, and the 3 to the 3rd power, well, the cube and the cube root will eliminate, or 3 can go into 3 one whole time, so that means I'm going to have a 3 on the outside. I'm going to put down a finger of space and write down the cube root, and what's left over is going to be 2 times 2, which is 4. Then I'm going to ask myself, how many times can 3 go into 8 evenly? And that's 2 times, with 2 left over. Because I know that 3 times 2 is 6, and 6 plus 2 is 8. And then 3 can go into 9 3 whole times, so that's going to be y cubed, with nothing left over. So your answer is going to be 3x squared y to the 3rd power times the cube root of 4x squared. And that is it. That's your answer. Let's go ahead and look at letter I. For letter I, we're talking about the square root of 16x squared divided by 81y to the 4th. So since 16 and 81 have nothing in common, and since x and y are not the same letter, what I'm going to do is I'm going to take the square root of the numerator and divide it by the square root of the denominator. The square root of 16 I know is 4. And the square would eliminate the square root when it comes to the x, so I'm left with 4x in the numerator. In my denominator, the square root of 81 is 9. There exists an invisible 2 on the outside, and I know that 2 can go into 4 2 whole times, so that's going to be y squared. So your answer is simply 4x over 9y squared. I'm going to let you do letter J on your own, and I'll certainly do that in class next time I see you, so I don't have that one circled. And let's go ahead and look at letter K. For letter K, R and S have nothing in common, so what I'm going to do is I'm going to take the 6th root of the numerator divided by the 6th root of the denominator. So I'm going to divide. 6 can go into 6 one whole time, so I have an R in the numerator, or the 6th root eliminates this to the 6th power, leaving us with just R. And then in the denominator, 6 can go into 18 3 whole times with nothing left over. So our answer is going to be s cubed. So r over s cubed is the entire answer. And finally, we have 56ab to the 3/4 power divided by 7a to the 5/6 power, c to the -3rd. So for problems like these, if the problem starts off with rational exponents, your answer will end with rational exponents. There is no need to turn them into roots. So what I'm going to do is work with each piece at a time. So 56 divided by 7, that's equal to 8. So my number is going to be 8. In my numerator, with respect to a, that's a 1. So this is really an a to the 1st power. And we're going to be subtracting it from 5, 6. So what I'm going to do is I'm going to change that exponent of 1 to a 6 over 6. So this is a to the 6 over 6 power times a to the, minus 5 over 6 power. So what I'm doing is I'm subtracting the exponents of a. Sorry about that. Then I have my b value, which is b to the 3/4 power. And then my c has a negative exponent, so I'm going to bring that up. So it's times c to the 3rd power. And nothing is left over in the denominator because I've already addressed everything. So now I have 8a, and then 6 minus 5 is 1, so that's to the 1/6 power, b to the 3/4 power, and then c to the 3rd power. And like I said, if you start with fraction exponents, your answer will end with fraction exponents. And you just use your properties of exponents that you've already learned in the past. So that is simplifying radical expressions. And now what we're going to do is we're going to add and subtract radical expressions. So just like yesterday, or in our last lesson, whether you watched it yesterday or whenever you watched it, in order for us to combine our like terms, you need to have like radicals. So everything needs to be the same in order for you to combine. And we treat our radicals as if they are variables. So we would look at 18 times the cube root of u minus 11 times the cube root of u as if this was like 18x minus 11x. That would equal 7x. So just like we have down here, we would combine the numbers in front. And our answer would be 7 times the cube root of u. And that is simply your answer. We just subtract the numbers in front. Let's go ahead and look at letter B. For letter B, we have a to the 4th, b to the 2/3, a to the 4th, b to the 2/3. So we treat these as if they are exactly the same. We don't really focus on what the variables are necessarily. They could be as complicated as possible, but as long as they are both the same, we just add the numbers in front. So 15 plus 8, that's 23. So our answer is 23, a to the 4th, b to the 2/3 power, and there's nothing further for us to do. Letter C is slightly more complicated. Just like the problem that we had before in our last lesson, you want to work with each expression individually until you end up with two expressions that are exactly the same. So looking at our first expression, we're talking about 10 times the 4th root of 7x to the 7th power. So I'm going to write down the number 10, and I know that I can't take the 4th root of 5, but 4 can go into 7 one whole time with 3 left over. So I have 10x times the 4th root of 5x cubed. So 4 can go into 7 one whole time, and then there's going to be 3 left over. And that's because if we have x to the 4th power plus x to the 3rd power, or times x to the 3rd power, we end up with x to the 7th. Okay, I've simplified my first expression. Then I'm going to write minus x, and I'm going to look at the number 80. Our goal is for us to come up with a number that we can work with that's a perfect to the 4th power. And I'm here to tell you that sometimes it's difficult to identify, so we're just going to work with the number 80. And most of us would probably say, okay, 80 is even, so I'm going to divide it by 2, and I end up with 40. 40 I could break down into 2 times 20, and 20 I can break down into 2 times 10, and 10 I can break down into 2 times 5. So what I have here is 2 times 2 times 2 times 2 times 5. That's 2 times itself 4 times, then times 5. So I'm going to write down the 4th root of 2 times itself 4 times, then times 5 times x cubed. Now your goal is to end up with a 5x cubed, and it looks like that's exactly what we're going to end up with. So if you ever get confused about what you want your roots to be, look at what you ended up in the first time. That's what you should end up the second time with. So the 4th root and the 4 will eliminate, and we end up with 10x to the 4th root of 5x cubed minus, well, the 4th root and the 4th power cancel out, leaving us with just 2x times the 4th root of what's left over, which is 5x cubed. Now it looks like our variables and our radicands and our radicals are all the same, so we simply combine our like terms. 10 minus 2 is 8. So that's equal to, that's equal to 8x times the 4th root of 5x cubed. And that is your answer. Finally, we want to find the expressions for the perimeter and area of a rectangle that has a length of x plus 3 and a width of 2x to the 2/3 power. So what I would recommend is drawing a picture. Draw a quick sketch of a rectangle. It doesn't have to be beautiful, it just has to kind of resemble a rectangle. And for this problem, we need to insert what our length and what our width is. So our length, we knew that that was x to the 3rd power, and our width is 2x to the 2/3 power. And we know that perimeter is when you add up all the sides together. So I'm going to add all sides together. Since this is a rectangle, we learned in geometry class that the opposite sides are congruent. So that's going to be an x to the 3rd power across from an x to the 3rd power, and this is 2x to the 2/3 power across from the 2x to the 2/3 power. And my perimeter is simply going to be adding up all the sides together. So I'm going to add x to the 3rd plus 2x to the 2/3 plus another x to the 3rd plus we have 2x to the 2/3 power. I'm going to combine my like terms, so I have x to the 3rd plus x to the 3rd, so that's 2x to the 3rd power. And then I have 2x to the 2/3 power plus 2x to the 2/3 power, which is 4x to the 2/3 power, and that's your perimeter. That's all you do. When it comes to area, area is equal to length times width. So I'm simply going to multiply my length times my width. So that's going to be x to the 3rd power times 2x to the 2/3 power. Whenever you multiply two powers with the same base, you add your exponents. So that means I have 2x to the 3 plus 2/3 power. So I'm multiplying two powers with the same base, I'm going to add the exponents. So I need to make a 3 have a common denominator of 3. So I know that 3 times 3 is 9. So this is really 2 times x to the 9/3 plus 2/3 power. So all I did is I changed this to have an exponent of 3 by multiplying 3 times the denominator. 3 times 3 is 9, and technically 9 over 3 is 3. 9 plus 2 is 11, so our answer is 2x to the 11 over 3 power. And that is simply your answer. So here is our perimeter. This is our expression for the perimeter. And here's our expression for the area. And that is it. That's our answer. If you have any questions, please make sure that you let me know. Please email me. Otherwise, I hope you have a wonderful day.